Ooh, fast Fourier transform. Wow. What's the good way to, I mean, any decent machine comes with the FFT hardwired in. So you might say, okay, I'll just use it, and that seems totally reasonable to me. But maybe you might like to see just on one board, what's the key idea? What's the little bit of algebra that makes it work? So I'll just have one board here for the FFT and the little bit of algebra. Simple, but once it hit the world, well, computer scientists just love the recursion that comes in there. So they look for that in every possible other algorithm now. I mean, this is like okay. Let me see that point. So here's the main point: that if I want to take the multiply by f of size 1024, the fast Fourier transform connects that full matrix to a half-full matrix. It connects that to the half-full matrix that takes the half-size transforms separately. So it's half-full because of these zeros. That's the point. That the 1024 matrix is connected to the 512 matrix. And what's underlying that? The 1024 matrix is full of e to the 2 pi I, the w, over 1024, right? That's the w for this guy. And then the w for this guy, for both of these, is e to the 2 pi I over 512. So if there's a connection between that matrix and this matrix, there better be a connection between that number and that number, because this is the number that fills this one, and this is the number that fills these. So what's the connection? It's just perfect, right? If I take this number, which is 1,000, one part of the whole circle, 1 over 1024, one fraction of the whole circle, what do I do to get this guy? To get 1/512 the way around the circle? I square it. The square of this w is this w. Let me call this wn, and this one wn. Maybe I'll use caps. Yeah, I'm using cap n. This is my w. This is the one I want, the wn, the n by n one. N is 1024. And the point is, everybody saw that? When I squared it, I doubled the angle. When I doubled that angle, the 2 over that gave me 1 over 512. Fantastic. Of course, that doesn't make this equal to that, but it suggests that there's a close connection. So what is this? Let me finish here the key idea then of the Fourier transform in matrix, in block matrix form. What's the key idea? So I'm going to, instead of doing the big transform, the full size, I'm going to do 2 half sizes. But what am I going to apply those to? I won't apply them. Here's the trick. These 2 separate guys apply to the odd-numbered coefficients, the odd-numbered components, and the even. So I have to first do a little permutation, an odd, and even. Even comes first always. Even means 0 to 4 up to 1022. So this is 0 up to 1022. And then come all the odd guys, 1 up to 1023. So this is a permutation, a simple permutation. Just take your 1024 numbers, pick out the even ones, put them on top. Right? In other words, put them on top where 512 is going to act on it. Put the odd ones at the bottom, the last 512, that guy will act on that. So there's 512 numbers there with the even coefficients. This acts. Okay, now we've got two half-size transforms because we're applying this to, I guess, to the y, to a typical y. Right? Okay. But I've just written f without a y, so I don't really need a y here. This is just a matrix identity. It's a matrix identity that's got a bunch of zeros there. Of course, that matrix is full of zeros. I mean, this is instant speed to do that permutation. Grab the evens, put them in front of the odds. Okay, so now I've got two half sizes, but that I have to put them back together to get the full-size matrix. And that is also a matrix, turns out to be a diagonal there, and a minus the diagonal goes there. So actually, that looks great too, right? Full of zeros, the identity, no multiplications, whatever. Well, these are the only multiplications. Sometimes they're called twiddle factors. Give it a fancy name, official sounding name, twiddle factor. Okay, so that diagonal matrix D, what's that? That diagonal matrix D is the power happens to be just the powers of W sit along D. 1 W up to W to the, this is Wn we're talking, the big W, and it's only half size, so it goes up to M minus 1, I guess. M is half of N. Everybody's got that idea. M is half of N here. I'll get that written on the board. M is 512, N is 1024. Here we have the powers of this guy up to 511. The total size being 512, because that's a 512 by 512 matrix. Okay, I guess I can remember somewhere being at a conference. This was probably soon after the FFT became sort of famous, and then somebody who was just presenting the idea, and as soon as it was presented that way, I was happy, I guess. I thought, okay, there you see the idea. Permutation, reorder the even, odd, two half-size transforms, put them back together, and what's happened here? The work of this matrix, multiplying by this matrix, which would be 1024 squared, is now practically cut in half, because this is nothing. And we have just this diagonal multiplication to do, and of course this is the same as that, just with minus signs. So the total multiplications we have to do, the total number of twiddle factors is this 512, and then we're golden. So we've got half the work plus 512 operations. That's pretty good. And of course, it gets better. How? What do you do once you have the idea of getting down to 512? What are you going to do now? This is the computer scientist's favorite idea. Do it again, right? That's what it comes to. Whatever worked for 1024 to get to 512 is going to work. So that now I'll split this up into, each 512. So now I have to do, let me write F512 will be now smaller, an I, and a D, and a minus D for the 512 size of F256, and then the permutation, the odd-even permutation P. So we're doing this idea in there and in there. Yeah, so it's just recursive, right? And now, if we go all the way, so you see why I keep taking powers of 2. Not natural to have powers of 2. 2 or 3. 3 is also a good, all this gets so optimized that some powers of 2 or 3 are pretty good. And you just use the same idea. There'd be a similar idea here for if I was doing, instead of odd, even odd, I was doing maybe 3 groups, but stick with 2, that's fine. Then, yeah, you might ask, if you were a worrier, I guess you might ask, what if it's not a power of 2? I think you just add in zeros. Just pad it out to be the next power of 2. Yeah, it's nothing difficult there. I think that's right. Hope that's right. Once this idea came out, of course, people started looking. What if the number here was prime, and found another neat bit of algebra that worked okay for prime numbers using a little bit of number theory. But the ultimate winner was this one. So maybe I just refer you to those pages in the book, where you'll spot this matrix equality, and then next to it is the algebra that you have to do to check it. The algebra, I can just say, because I want you to look to the right spot there. Maybe I'll take out the great, this is sometimes called after Parseval or some other person. Yeah, the algebra, let me start the algebra that made this thing work. It is the algebra, we want the sum, when we multiply Fourier f times something, we want the sum of w to the jk, right? That's the coefficient, that's the entry of f times ck, summed from k equals 0 to n minus 1 to 1023. That's the yj that we're trying to compute. We're computing 1024 y's from 1024 c's by adding up the Fourier series when we multiply by f. This is f. This is the equation y equal fc written in with subscripts. Okay. So this is what the matrices are doing. And now where do I find that 512 thing? Or how do I get m into the picture? Remembering that wn squared was wm, right? That's what we saw. This is the big number. This is half of it. So this is a little bit of the part around the circle. When I go twice as far, I get to the other one. Yeah. So that's the thing that we got to use. Everything is going to depend on that. So so this was Wn, of course. This is the n by n transform. So now comes what? What's the key idea? Key idea is split into even and odd, and then use this. So split into the even ones and the odd ones. So I write this as 2 separate sums, a sum for the even ones, Wn to the, now the even ck, so I'm going to multiply by c2k. These are the ones with even, and the sum is only going to go from 0 to m minus 1, right? This is only half of the terms. And then will come the other half, plus the same sum of, but I didn't finish here. Let me finish. So I'm just picking out, I'm taking, instead of k, I'm doing 2k. So I have j times 2k here. And now these will be the odd ones, c2k plus 1, and omega n to the j 2k plus 1. It's a lot to ask you to focus on this bit of algebra. I hope you're going to go away feeling, well, it's pretty darn simple. I mean, there'll be a lot of indices, and if I push it all the way through, there'll be a few more. But the point is, it's pretty darn simple. For example, this term. What have I got there? Look at that term. That's beautiful. That's Wn squared. What is Wn squared? It's Wm. So instead of Wn squared, I'm going to replace that Wn squared by Wm. And the sum goes from 0 to m minus 1. And what does that represent? That represents the F512 multiplication, the half-size transform. It goes halfway, it operates on the even ones, and it uses the m. It's just perfectly. So this is nothing but the Fourier matrix, the m by m Fourier matrix, acting on the even c's. That's what that is. And that's why we get these identities. That's why we get these identities, because they're acting on the evens. That's what the top half is the even guys. Okay, this is almost as good. This is the odd c's. Here I have, now do I have Wm here? I got to have Wm. Well, you can see. It's not quite coming out right, and that's the twiddle factor. I have to take out a Wn to the power j to make things good. And when I take out that Wn to the power j, that's what goes in the D, in the diagonal matrix. Yeah, I won't go more than that. You couldn't... There's no reason to take it to do everything here on the board when the main point is there, and then the point was recursion, and then let me complete the recursion. So that I recurse down to 256, then 128, then 64, and what do I get in the end? What do I get altogether once I've got all the way down to size 2? I have a whole lot of these factors. Down in the middle, what the part that used to be hard is now down to F2 or F1 or something. So let's say F1, 1 by 1, just the identity. So I go all the way, 10 steps from 1024, 512, 256. Every time I get twiddle factors, every time I get p's, a whole lot of p's. But the F512, what used to be the hard part, has gone to the easy part. And then what do I have? I've got just a permutation there. And this is the actual work. This is the only work left, is the matrices like this for different sizes. And I have to do those. I have to do all those twiddle factors. So how many matrices are there? It's the log, right? Every time I divide it by 2. So if I started at 1024, I'd do 10 times. 10 of those matrices have me down to n equal 1. So I've got 10 of these. So and each one takes 1024, or maybe only half of that. Actually, only half, because this is a copy of that. I think the final count, and can I just put it here? This is the great number. Is each of these took n multiplications, but there were only log to the base 2. Oh, no, each of them took half of n multiplications, because the d and the minus d are just, I don't have to repeat. So half n for each factor, and the number of factors is log to the base 2 of n. 10 for 1024. So that's the magic of the FFT. Yeah, yeah. Okay. It's almost all on one board, 1.5 boards to tell you the key point, odds and evens, recursion, twiddle factors, getting down to the point where you only have twiddle factors left, and then those multiplications are only n log n. Good? Yes, right. Okay. Now, that's discrete transform. The theory behind it and the fantastic algorithm.